Hello and welcome back. This video is part 2 of our series on real-time signal processing as it applies to the MonkeyJam. But like I said before, this can apply to any signal, not just a guitar signal. So we're going to look in this video at basic tone controls. So how do we make what are called tone controls? Like you might have like an amplifier to, maybe boost or cut, different frequencies. So I've pulled up here, I have an old twin reverb, schematic, the old hand-drawn schematic. And this is a tube amp, so the power control devices are tubes. And there is a handful of resistors and capacitors and, transformers that make up the other parts. Now, I'm going to zoom in a little bit here, and I apologize if this is a little gritty, but the input to the twin reverb, this is a common what's called tone stack. And you notice there is a couple capacitors. Let me grab my red pen here. Right here, here and here. And we have some potentiometers right here. A lot of the tone, not all of it, comes from this tone stack. That's what gives some of the knobs in the front panel. This component of the tone, which I'm saying there's nonlinear stuff, we're going to look at the tubes later, but this part of it, kind of like the EQing, although this is a very rough EQ, comes from these components. So what we're going to look in this video is how do we model that? How do we get that part into, into the software? So all of the passive components, called resistors, caps, we're going to call these linear components. So, and I'm going to refer to them as linear. Now, we can have arguments about the non-linearities of these, but for now, we're just going to look at them as like ideal components. So, what does linear mean? So you may have had a DSP course, you may have not. So we're going to look at linearity kind of from more of the mathematical point of view. So the way you do it in any of like a signal processing or a signals and systems course, is that we consider this black box system. We have an input signal coming in this output signal. And we put some screwy thing in, and we get something else out. All right? And we call this the system, and it's called H of Z. Now, for now, if you've never had a DSP course, don't even worry about what H of Z. That's called a transfer function. But for now, we just call this the system. All right, we have a black box, we put a signal in, and something else comes in. In signals and systems, in a DSP course, you learn about what's called a linear time invariant system, an LTI system. And there's some basic properties of what an LTI system is. And here's how you kind of can define it, is that if you have some input signal going into a system A, which is red, and a system B, you can reverse the order of the systems, put system B, system A, and it's equal. You get an equal input and output. It's as simple as that. All right? That's easy enough. Now, here's another useful property of linear time invariant signals. All right? If I have two input signals and I have one system, I can put each one through the system and add them and get to an output signal. Or I can reverse the operation. I can add the input signals, then put it through the system. They'll be equal. That is a way of defining kind of qualitatively or graphically a linear system. Here's another. Let me go back here. Kind of system is that if I have something like this, an input signal goes in the system A, and then I have an input signal going into system B. We add them, then multiply them, or you get an output signal. I should be able to take this multiply and put it here and here and reverse the order, and it should not even matter. So those are some ideas of, some principles of a linear system, is that, as you can see, ordering should not matter in a linear system. So linear systems have a certain way which we characterize them. And the way we characterize any linear system is that if we put an impulse into it, meaning a signal like a little blip, think of like a gunshot or like, a hammer hitting something, we get some sort of response, all right? And we call this the impulse response, all right? It turns out if we take what's called the Fourier transform of this impulse response, because we're looking here at time waveforms in t. This is a waveform over time going blip, and this is the response. The Fourier transform of the impulse response, that's the frequency response. That's kind of like how it responds. The system changes the amplitude and phase of the different tones, in that signal. Now, there's a couple of structures that are very common that you'll see for a digital LTI. The first one is called a finite impulse response filter. And this is a little what's called signal graph of a finite impulse response filter. So here's what the blocks mean. Is that we have our signal, which we discussed in our first video, x of n, our current input, and over here we have our current output. Is that we have a block, z to the negative 1 is a way of saying delay by one sample. So if we take and say multiply our current sample by one coefficient, delay it by one, multiply it by another, add them, go on so and so forth, we get something called a finite impulse response filter. And let's look at this in a different way. To do it in real time, here's the equation. Our current output is just our current input times some coefficient plus a previous input times a different coefficient plus, so on and so forth. And if you do this, it turns out you can create a filter, all right? And the magic is picking out these filter coefficients. Now, why do we call this a finite impulse response filter? Is that, let me get out my pen here, is if I have an input, and I'm just going to draw these little stems here. This is like a stem plot. I'm going to say this is a value of 1, and if we're down here at 0, if I put this into an FIR filter, we get out, if you imagine, okay, the first time I run through this, I get, my first coefficient. Then the next time I compute, I'll get the next one out, so on and so forth. But because the finite impulse, there's only so many coefficients, eventually this one propagates through the entire filter, and over time, it goes to 0. So the impulse response, numerically has a finite length, and it's equal to the number of what are called taps in the filter, T-A-P-S, taps. Taps in the filter, all right? So that's simple enough to understand. Now, there is another type of filter called an infinite impulse response filter. And what that means is if you were to hit the input with your impulse, is that even though we have a finite size in the number of taps in the filter, the impulse response never goes to 0. It goes on infinitely. Now, it might decay to something very close to 0, but the impulse response isn't related to the number of taps. It's completely decoupled. Now, here's a drawing. This is from an Intel website of the signal graph of an IIR filter. It's identical to a finite impulse response filter, except that a finite impulse takes our current input, previous inputs, scales them, and adds them up. An infinite impulse response filter takes the output of the filter and then feeds that back and does the same operation only to the outputs of the filter. So what we have here is now negative feedback. So we often call this the feed forward term. And we call this the feedback. And by doing the feedback term, we can get some very interesting things to happen with a very small number of coefficients. Now let's look at it. Yeah, so here once again is the this is what's called the difference equation. The difference here, no pun intended, is that we have the current output is dependent on the sum of the scaled sum of all the previous inputs with some scale factors, but we also add in previous outputs to our signal. We get a feedback. All right, and the idea is that we execute this computation every time we get a new sample, every time. And so we can turn an IR filter and FIR into an FIR just by simply removing the feedback terms. And that makes it an FIR. Now, the reason it's infinite impulse, by adding negative feedback, that's what allows the impulse response to essentially go on forever, because we're continually taking what we already had and feeding it back. And to the point, it's when you study in a signal processing class infinite impulse response filters, it's possible for these filters to be unstable, meaning when you hit them with an impulse, they will oscillate forever, and they will even exponentially grow. And there's a lot you can do to ensure stability, but the key is in picking, these coefficients. So you can actually create oscillators, from IR filters. But they're very powerful in that we can get nice tone controls with, very few coefficients with an IR filter. And we can really do neat stuff. You can also do with FR, but we're going to see there's some trade-offs to be made in choosing which structure we use. So here's some quick notes. Now, it's impossible to do a whole DSP course, in 20 minutes here. But here's some things to take away. FR filter has finite impulse response length. That's the number of coefficients. It turns out we can make a filter that can model just about any linear system, but here's the trade-off. It takes a lot of coefficients to get a good model. All right, it can take a lot, like 50, 100, 250. That's a lot of computations in every cycle. And you can see, if I just go back to IIR, the only thing that you have to do when you compute, there's kind of two functions. Here's a multiply, and here's an add. So a lot of DSP chips that do DSP, really when they say do DSP, all they're doing is they have an accelerated, essentially an accelerator to do multiplies and adds. They can do it in one step. IIR filters, on the other hand, have an infinite impulse response, and they'll go on forever. A stable filter will decay to 0 over time, but you can make oscillators. All right, IR filters use feedback from the output, and they can oscillate out of control if you get the wrong coefficients. And I really hope when you're playing around with the software you do that, because you can see you can make some really interesting stuff. IR filters, what your trade-off is, you get fewer coefficients at the expense of sensitivity to the design for stability. So it turns out IR filters, you need a lot of precision in the coefficients, for example, of doing low-frequency filters. And that's actually important in guitar because you need a lot of precision in the coefficients to tightly control where the cutoffs and whatnot are in your filters. But if you can get the implementation right, it doesn't take a lot of coefficients to do it. So the magic, all of the magic, without going to the math, is in picking the coefficients or the taps. All right, and this is where a DSP course will take you for a month. And how do you do that calculation? The good news is there's lots of tools for doing the math. There's lots of cookbooks. Now, it turns out that you can actually model an operational amplifier in an active filter pretty easily with an IIR filter. And there's actually ways that if you have an analog filter design, you can go and find the digital equivalent that's pretty close. So all of our audio filters, like what are called shelving filters or tone controls, low pass, high pass, notch, we can do them with IIR filters or FIR. A useful IR filter is called a biquad. What a biquad is, it is a second order filter, meaning by second order, meaning there's only, let me go up to the picture here. We only have a limited number. We only go to y-2, n-2 in our feedback terms. But IR biquads are nice because they're used for building blocks, and they're easy to chain up. And it turns out when you design IR filters of very high order are very difficult to design because the coefficients are very, there's a lot of sensitivity in your output frequency response, even if your coefficients change a little bit. Biquads are useful because second order filters are least sensitive to error in your coefficients, and it's easy to map analog filters into biquad structures. There's actually been a lot of work done. Now there is a link here, and I'm going to pull it up for you. I have a really nice reference here, this Audio EQ Cookbook by Robert Bistro Johnson. This is an absolutely beautiful reference for IIR biquads. So what he did was took some very common, audio EQ types or audio filtering types and kind of converted them into digital form. So this has been on the internet for as long as I can remember. But what's nice is he has a cookbook that he tells you, okay, here is the difference equation, and then he'll give you a cookbook to figure out the coefficients. So if you read through this, you give it things like sampling frequency, Q, bandwidth, and it'll do all the work for you. Now, the types of filters he has is low pass filter, high pass, band pass filter, notch filter, all pass filters, shelving filters, so on and so forth. Now, the way he did this is that he used something called the bilinear transform. The bilinear transform, if you've never heard of it before, it's a good thing to study. It's a nice way of mapping filters and transfer functions in the analog domain into the digital. And that's where it all came from. Now, the MonkeyJam software has this kind of feature already built in. So the first thing I'm going to show you is I have a program, and the first thing I'll bring in here, it's on GitHub. And it's called Biquad Filter View. If you find eHues Biquad Filter View, you can get the source and executable that for this program. And what this program does is it allows you to visualize. Let me bring this into your. Let me bring this into the window here. It allows you to visualize all of these different types of filter types from this cookbook. Everything is for the cookbook. So, for example, here, let me pick something out. There's like the high shelf filter. I have a graph here, and just so you can see it, I superimposed frequencies of like the low E string, the high E at the 12th fret, the high E at the 24th fret to give you where those frequencies are. It shows you the difference equation right here, and then gives you the coefficients. All right, so let's just play around with this. Let's say we're at a high shelf. Notice it's flat, and what I'm doing is I'm going to move the dB gain down 12 dB. So the green is our magnitude, so we can see at a cutoff frequency of 100 hertz, we get our negative 18 dB gain. So this tool allows you to kind of play with it. you know, and move these numbers around just to get a feeling for what how these filters kind of work. Now I can play with the Q. The Q is definitely an EE term of a quality factor, so you can create little resonant peaks. And it allows you to play with sample rate and whatnot. So go ahead and play with this. Like, let's look at a peaking EQ. In this case, we can create like a notch in our frequency spectrum, or we can go the other way. We can create a little peak. Notice things like what the Q does. We can widen it out, you know, and kind of play around. And so this is just kind of like a little sanity check, a little tool just to kind of allow you to visualize it and see it with respect to frequencies of the guitar. All right. Now let's close that. So right there, that's a good introduction to tone controls. So you have everything you need now to make tone controls. Now, I don't want to go into too much. In another video, we're going to look at some example code of some basic tone controls. But I just want to get your capture your interest here in showing you some structures that you're going to be able to use to play around with. Now, I'll tell you right now that you don't have to code, for example, these IR filters from scratch. I have nice C functions that'll generate all of these coefficients for you, so you can just kind of play around with like the numeric values. And you don't have to necessarily write code from scratch. I kind of did that work for you, and you can just get right to playing with the tone controls. But it'll give you some building blocks that you can build off of. So that's all I have for today. Tune in next time for looking at nonlinear type processing.